Hello everyone, my name is Ali Safari and I'm a PhD student at the University of Washington. Sing Young and I will be presenting our paper with this title, Battery-Free Camera Occupancy Detection System. As we all know, camera-based occupancy detection systems are pervasive, and the biggest challenge they face today is that the cameras are power-hungry and the detection process is done either by a powerful processor or on the cloud. Let's look at a specific example. Wireless cameras are popular for security applications and smart home monitoring systems. Here is a 1080p wireless camera that uses a large solar panel for its operation, but the battery may need to be replaced or charged. This is even worse in indoor setups because the panel collects less energy indoor. Given these power requirements, here is the challenge we articulate. Can we design a human occupancy detection system that uses battery-free cameras, a fast and accurate algorithm, and a chip processor to sense human presence? If we can do this, we can now have a battery-free camera that streams video to a hub for human occupancy detection. Here is a list of our contributions. We implement wireless battery-free cameras that harvest energy from ambient light. We deploy YOLO V5 model on an embedded system for human occupancy detection. And third, we measure the speed, detection accuracy, and reliability of the proposed system. Let's see, now we know the contributions, let's see how we made the first contribution possible. Here is the block diagram of our sensor node. Our image sensor has four main sections. First, a backscatter communication block to transmit the images to the hub. Second, a microcontroller to handle the operation of the image sensor. Third, a harvester to collect energy for the camera's operation. And fourth, a low-power image sensor to capture low-resolution images. Backscatter communication is a low-power wireless technology wherein a transmitter generates a carrier signal, a sensor node reflects the carrier, and a receiver decodes the sensor node data. Since the sensor node does not need to generate any signal to communicate with the receiver and only reflects the carrier, the power consumption for data transmission is low. Here we have our transmitter that generates the carrier. We have our sensor node that has the camera, and we have our hub that has a receiver board and a Raspberry Pi 4. We keep our system in sleep mode and wait for the hub to request an image. Our camera is equipped with the low-power ASK radio to receive commands from the hub and wake up the sensor. Once the command is received, the microcontroller enables the image sensor and records one image. The MCU breaks the raw image data into 12 portions for data transmission. Please note, we do not perform any compression using the sensor node processor because this process is very power hungry and slow. We use the TI BQ25570 harvester IC to collect energy. We store the harvested energy in a supercapacitor. Since our system is low power, a small solar panel can provide enough energy for the operation of the camera. If we use a larger solar panel or set up the system in a room with a higher light intensity, we can collect more energy, which means the camera can capture images more frequently. We use high-max image sensor to capture 120 by 120 grayscale images. Per each pixel, the image sensor outputs 8 bits. Since this image sensor is low power, it does not have any noise removal block to improve the quality of the images. So, we place a white paper in front of the lens and record hundreds of images. We take an average across these images to estimate the noise. We subtract this noise from the images that we record to remove the static noise. Here we have the image before enhancement, and this one is the same image after enhancement. Now we know how the battery-free cameras work. Let's measure the power consumption of the camera. We use a 2.2 ohm resistor in series with the camera and measure the voltage of the resistor. This voltage is 2.2 times the current that the camera and the resistor consume. We analyze the voltage data that the oscilloscope records and report the power numbers. Since the resistor value is small, we can assume that the camera consumes the total current. This table lists the results of our measurement. When the camera is in sleep mode, the power consumption is 30 microwatt. To take a picture, the camera needs 6.5 millijoules. And to transmit that image, it needs 3.82. To show that our harvester can support the camera, we use 2 solar panels as the input of the harvester and measure the update rate of the camera. When we use the small one, the update rate is 280 seconds, which means every 280 seconds, the camera can send picture to the hub. And if we use the bigger one, we can send image to the hub every 17 seconds. That was my presentation on the hardware side of the paper. Sing Young will be presenting the second half of the paper.
Thank you, Ali, for the first half of the presentation. Hello, everyone. My name is Sun Young Tan from Iowa State University. I'm also the co-first author for this paper, and I will be presenting the second half of the presentation, specifically on the algorithm side of the paper. Implementations and deployments. So before jumping into the algorithm, we'll start things off by looking at a quick overview of the system. In this slide, I showed a simple infographic flowchart of our proposed system, end-to-end from signal transmission to the final detection. We have already seen the first half of the system from Ali, who focused on the sensor and system hardware design. So now my focus is on the second half, which is to perform occupancy detection on the images that we captured. So to do that, we utilize the state-of-the-art YOLO V5 model and the deployment to the Raspberry Pi by converting the trained model to a TensorFlow-like format. So what is YOLO V5 model? So in this slide, we will dive a little deeper in explaining the YOLO V5 detection model. So starting from the top left, the goal of the detection model was to take in an image and accurately outputs the bounding boxes that captures the presence of the occupant in the frame. So detection model usually contains three main components: the model head, neck, backbone as illustrated in the model anatomy on the bottom left. So from bottom up, the model backbone is a feature extractor, which its main role is to extract rich and useful features from the input images. There are many backbones that was being developed and proposed over the years, and in YOLO V5, the cross-stage partial network or CSP network is used as the backbone. Uh, Moving up, we have a second component, which is the model neck, and its primary function is to generate multi-scale feature pyramid, and that allows the model to detect objects in a different size and scale. And in YOLO V5, the path aggregation network or PANet is used as the model neck. The last component, which is the model head, its main function was to take in the feature map that was generated and outputs the bounding boxes prediction by applying the anchor boxes on the feature map. So YOLO V5 was proposed in a few sizes: S, M, L, and X, which each arranged in an increasing model size. For our application, we use the S model, the smallest model, as it has the smallest model size and the fastest inferencing speed. So the model weight size is only 14 MB, and it have only 16.8 gigaflops and 7.25 million parameters in the model. To train the model, we capture images using the proposed system, and we annotate the occupants in the images with bounding boxes. We perform a few data augmentation to the collected images, including varying the brightness, mirror, and mosaic augmentation. So with the augmentation, we prepared around 3,000 training samples, 430 validation samples, and around 860 testing samples. The model was trained using a Tesla T4 GPU, and the final trained model was converted into a TensorFlow Lite format for deployment on the Raspberry Pi. The conversion to TensorFlow Lite format allows us to use a lightweight TensorFlow Lite model interpreter that was specially built for inferencing on embedded systems. After deploying the model on the system, we tested the system by performing a few experiments in different locations, including the lab and the living room and kitchen in my apartment. So for each location, the system was tested up to 10 hours with up to 2 occupants in each location. So in the experiment, I have placed a sensor and receiver up to 30 feet apart, and the system communication is still working perfectly. So in the living room images, we can also see that there are some occlusion cases where only the top half of the occupant's body is visible in the images. So in terms of the inferencing speed, we are able to achieve around 100 millisecond inferencing time per image on the Raspberry Pi with only 4 GB of RAM. So the table on the left shows that in each of the location, the system collected up to around 3,000 images during the experiment, and we achieved more than 90% prediction accuracy for all the location. In the last row of the table as well, we ran the experiment for up to 5 continuous days, and we've collected up to 32,000 images, and we have a prediction accuracy of up to 92.72%. So in conclusion, in this paper, we propose a power-efficient and high-performing occupancy detection system. In the system design, we use a solar energy harvester to power the low-power camera sensor, and we transmitted the images using a backscatter communication technology. And in terms of the algorithm, we implemented the state-of-the-art YOLO V5 model on the Raspberry Pi, and we were able to achieve a great performance with a low inferencing speed. In the future work, we will try to further enhance the system's performance by coupling it with motion detection either by equipping some motion sensors or implementing image differencing. Image enhancement is also another direction that we will look into to further improve the image quality for a better prediction. And with that, I would like to conclude my presentation by thanking our reviewers for the constructive feedback and our sponsor and funding agencies for funding our research. If you have any questions, our email is available in the slides and in the paper, so feel free to email me or Ali with any questions that you may have. So I would like to thank everyone for your attention and have a great rest of the day. Thank you.